Hello students, now in this video we will discuss about the free radicals, the carbon free radicals. A carbon free radical is a carbon with an odd number of electrons. A carbon free radical actually it has 7 electrons in the valence shell like this one, and it's formed when there is a homolytic bond fission between the atom A, which is bonded with the carbon, and the bond fission occurs so that the one electron goes with the atom A and the one electron goes with the carbon, and now you get the carbon with 7 electrons in the valence shell. You have here the carbon with 8 electrons. When an atom A is lost here as a free radical, you get the carbon with 7 electrons. It's a neutral molecule, it's a neutral species, and like carbocations, it's also electron deficient, right? Because it has only 7 electrons in the valence shell. Okay, so the free radical behaves, in terms of stability almost similar in the same pattern as we find for the carbocations. Because carbocation is also electron deficient, the free radical is also electron deficient. The difference here is the carbocation is positively charged, it has that is 2 electron deficient. The free radical is a 1 electron deficient species, and it is a neutral molecule, but both are electron deficient species, and the stability order will see that will be almost the same pattern. Now what about the shapes and the hybridization? Alkyl free radicals, the carbon with the free radical, right? If it is attached with the alkyl groups, okay, then the hybridization is always sp2. It's a planar molecule. That means the sp2 hybridized carbon free radical is like this. It has 3 alkyl groups like this, or you can say 3 hydrogen atoms here. The hybridization is sp2 is a planar, and one of the p orbital, unhybridized p orbital, okay, that carries an electron there. So it has sp2 hybridization, and the bond angle will be 120 here. But if you attach electron withdrawing groups like the fluorine with the carbon, then its hybridization changes from sp2 to sp3. So the carbon with 3 fluorine atoms, its hybridization is sp3. However, the alkyl free radicals are generally sp2 hybridized. If you look at the carbocations, we know the carbocations, they have the hybridization of sp2, the carbocation with sp2 hybridization, and the carbanion has a hybridization of sp3. So like a pyramid carbanion, and the carbocation is sp2 hybridized, it is planar. While as free radicals, their hybridization is between sp2 to sp3, depends what kind of the groups are attached there, right? If it is an alkyl, then it's sp2 hybridized. If it has alkyl groups attached here, then it will be the sp2 hybridized. But if it has electron withdrawing groups attached, then the hybridization will be sp3. And among the alkyl groups, among the alkyl free radicals also, if we increase the number of alkyl groups, then some polarity is lost there, right? Like this. If we have a free radical with the 3 hydrogen atoms only, it's more planar. It's almost 100% planar molecule. Whereas if you go on increasing the alkyl groups here with the carbon, the polarity is lost, right? Now the trialkyl is actually less planar, right? So there is some difference in the planarity also, but the hybridization is obviously the sp2. However, the molecule, the free radical with 3 alkyl groups, and the carbon with a carbon with the 3 hydrogen atoms, there is a difference in the planarity. Hybridization is same, it's sp2, but there is difference in the planarity. This molecule is more planar, and if you go on increasing the alkyl groups, the planarity decreases. And if you attach the electron withdrawing groups like fluorine, then hybridization again changes from sp2 to sp3. Now coming to the next part, that is the stability, which is very important. As I said that the free radical is electron deficient. Okay, free radical is actually an electron deficient. It contains 7 electrons in the valence shell. It needs 1 more electron. So because of its electron deficiency, we can say that its stability will increase if you attach a group that can donate electrons to the free radical. If we attach electron donor group, an alkyl group, say for example, because it is electron donating group, it has a positive inductive effect. It will provide electrons, so some kind of electron deficiency will decrease with the free radical, so it will be more stable. So in general, we say that electron donating groups or electron releasing groups can increase the stability, while as electron withdrawing groups, they will decrease the stability. A free radical with a group that withdraws electrons from the free radical will make it unstable. And second point, if you can delocalize the free radical, it also provides the stability. Means resonance also helps in the stability of the free radical. Due to the resonance, the free radical will be delocalized, and therefore it can provide it stability. So which means that benzyl free radicals or allylic free radicals are very much stable, because in those compounds, in those free radicals, due to the resonance, free radical will be delocalized, and that provides the more stability. So we got there here a conclusion that electron donating groups increases the stability, withdrawing groups decrease the stability. So therefore, among the alkyl free radicals, we can say the tertiary is more stable, right? Because in tertiary free radical there are 3 alkyl groups attached, so that will be a more stable one. Then the secondary, which is only 2, so the order will be like this. The tertiary free radical is more stable because it has 3 electron releasing groups, then secondary, then primary, then the methyl free radicals, right? So this is actually the same order as the carbocations. We also know that in the carbocations the order of stability is tertiary is more stable than secondary, then primary, and then the methyl free radical. So same order for the free radicals as well. So the effect is same, right? Electron releasing groups increase the stability, electron withdrawing groups, they will decrease the stability. The next point is about the resonance. Resonance also provides stability. If you remember, for the carbocations, the electron pair shifts toward the pi bond shifts towards the carbocation. In the carbanion, the pi bond it shifts away from the carbanion, right? But in free radicals, if you have a free radical, it will also be delocalized by the homolytic bond fission here. The homolytic bond fission will occur here in this pi bond as well, and now you get actually a free radical over here, then a single bond now CH, and then a double bond CH2, right? Which means the first radical, it goes to the second, and second will go back to the first, again by homolytic bond fission here also, right? So resonance also provides stability. We can also see for the benzyl free radicals. Again here the homolytic bond fission will occur, electron goes here, 1 electron goes here, and you can draw a canonical structure like this, right? For this one, it will be a double bond here, right? And a free radical will be here, and you have a double bond here and here. And then you can, these are the different canonical structures here. This is the second one, and you can again change it back into the third one here like this. Again, a homolytic bond fission will occur here, and a free radical will be at the para position. So you get a double bond here, a double bond already here, and a here. The free radical goes to the ortho position first, then it goes to the para position, and then it is delocalized again to the next one, You see here the free radical is, it will be like this, and the free radical will be here generated. Double bond is here, double bond is here, and the double bond is here also. And again this is an ortho position, and again you can change it back into the first one by the homolytic bond fission. A double bond is inside the ring, and you get the free radical over here, which means that if you attach a benzene ring, the free radical, okay, gets delocalized over ortho, para, and the ortho position. So one benzene ring provides 3 more canonical structures. So total number of canonical structures for this one is 4, right? So total number of canonical structures is 4. And if you attach 2 benzene rings, right, so if you have a biphenyl, okay, like this, if you have a CH and the 2 phenyl rings are there attached, so the number of canonical structures for this molecule will be 3 from here, 3 from here, and 1, the original one. So total will be 7. So biphenyl contains 7, it has 7 canonical structures, which is more stable than the phenyl. And then the triphenyl, right, that is highly stable. Triphenyl one, very much stable, correct? So overall order, we can say that benzyl free radicals are more stable than allyl, okay, and then the alkyls one. Among the alkyls, this is tertiary, then secondary, right? This is tertiary, this is the secondary, this is the primary, and this is the methyl free radical, or you can see the 0 degree, right? So benzyl are more stable because aromatic compound, you attach a ring, more resonance is there, so that is why it is more stable than the allyls, right? Okay, so this is the overall order of the stability of the free radicals, almost a similar pattern as we find for the carbocations, right? So let's now do some questions, a couple of questions here on the stability order. If you have a free radical like this, for example, you got a free radical like this, you have a free radical here, and then you have another free radical here, and then you have a free radical here like this. The order of stability of the free radicals will be, the B is more stable because this is the benzene attached to it, so this is, aromatic free radical, okay. So benzyl free radicals are more stable. Then this one is a tertiary one, and this one is a secondary one. So B is more stable than the A, than the C. This is the decreasing order of the stability. Decreasing order of the stability of the free radicals. Another molecule, for example, we got a free radical, the CH3 CH2 free radical here. This is the one, and the second one is CH2 Cl CH2 free radical, right? The difference here is, this is 1 degree, this one is also 1 degree, but the difference is we got a chlorine here attached to this one, which is electron withdrawing groups, and electron withdrawing groups, they will decrease the electron density, and we know the electron withdrawing groups decrease the stability of the free radicals also, right? So electron releasing groups can increase the stability, electron donating groups, they will decrease, right? So that's why here the A is more stable than the B. The first one will be more stable than the second one. Okay, so let's discuss this one. A free radical here, and a double bond is here. A free radical is here, and double bond is over here. Any difference? Yes, there is a difference. We find that the first one, it's not a conjugate system. The free radical is not present at the allylic position. You have a free radical first, then a single, then again a single, so then a double bond. So you cannot have a resonance here. So there is no resonance in this one, right? No resonance is possible here. correct? No resonance is possible here, whereas in this free radical you can delocalize it, right? Because you have a free radical, then a single, then a double bond. So the free radical is actually present at allylic position. So this is a conjugate system actually, right? This is a conjugate system, and the resonance is possible over here. And what you think, I think it will be alike. It will be double bond will be like this. The free radical will be here, right? So now this is a secondary free radical, and this is the tertiary free radical. Okay, it will go back here, right? It will go back here and form with the first one back. So you got the two canonical structures, and the resonance is possible here. There is no such resonance possible here because you have two single bonds continuously. So this is not a conjugate system. This pi bond cannot delocalize the free radical, right? So that's why the B, the second one, is more stable than the first one. This is the order of stability. Now let's take another question here. Say we have a CH3 single bond, CH, the benzene ring attached to it, and then the CH3 single bond, CH, right? So among the two, we find which is more stable, the first one or the second one. The first one is more stable. Why? Here because the free radical can be delocalized by this aromatic ring, whereas there is no such resonance possible here because you find the two single bonds, free radical, single bond, right? So this cannot be delocalized. You know, the resonance has no effect here. So there is no resonance possible here, right? Whereas you can delocalize over here. In this one, the free radical can go to the ortho, para, and again to the ortho position, but there is no such resonance here possible, correct? So you can have here, you know, the three more canonical structures, whereas there is no resonance possible in this one. That's why the first one is more stable than the second one, right? Because for the resonance, you know, actually if you have a free radical, then you have a single bond, then you should have a double bond after that, right? If you have a system like this, if you have a free radical, then a single bond, then again a single bond, and then there is a double bond, then this double bond cannot delocalize it here, right? So there is no resonance possible in this system. You need to have a free radical at the allylic position, or you can say it should be in the conjugate system, right? Double bond, single, and the free radical, right? You can, you know, just like the carbocations, double bond, single bond, and the positive charge here, right? A double bond, single bond, or the negative charge here, right? So you can delocalize everything which is at allylic position to the double bond. But in this one, there is no resonance possible. So it's the same thing here. The free radical, single, and the single bond, two single bonds, then the double bond, so no resonance is possible. Whereas resonance can occur here, right? So this is actually okay. Now let's take one more question over here. Okay, say we have a molecule like this, CH3 CH 2 CH 2 free radical. This is the first one, and the second one is like this, CH3 CH. We got the Cl here and the CH2 here, right? And then the third one is like this, CH2, the Cl here, and then the CH2, and then the CH2 free radical, and then the last one is you have a CH Cl, and then the CH Cl, and this is the CH2, right? So what will be the decreasing order of the stability? Which is the most stable one? All of them are primary. And the second point is we find in these three, B, C, and D, we find the chlorine, which is electron releasing group. Okay, so electron withdrawing group, it withdraws electrons. Here we find the two electron withdrawing groups. So that means the first one will be the most stable. Why? Because it does not have electron releasing group. Here it does not have electron withdrawing group, correct? So you have a chlorine here, they will decrease the electron withdrawing groups, they decrease the stability, right? Electron donating, electron releasing groups increase stability, electron withdrawing groups they decrease. So you have electron withdrawing group here, you have electron withdrawing group here, and in this one also, so they will decrease the stability. So that means the first one is the most stable one. So A is the most stable one, right? And among these three here, we find you have a one chlorine here, and this contains two chlorine. So this will be the least one, right? Because it has two electron withdrawing groups. So the least stable, this one, D. Out of the B and the C, you find the chlorine is slightly closer here than the C, right? Here the chlorine is closer, it's at the carbon number 2, here it is at the carbon number 3. The chlorine is attached at the carbon number 3, here it's at the carbon number 2. So this is a closer here, so it has a dominant effect here, more effect here than the B, than the C. Therefore the C will be more stable because it's slightly away from the free radical, so its effect on the free radical will be very, very less, okay, as compared to the B. So that's why the first one is more stable, A is most stable, then it is the C, and after that it is the B, and then after that it is the D, the least one, right? This is the decreasing order of the stability of the free radicals, right? So hope you got the concept. Thanks for watching the video. See you in the next video. Bye.